I don't know if I can listen to Nicolas. Is it me or?
No, Nicolas.
Sorry,
Okay, okay, perfect. Okay, thank you.
sorry for that. I got my micro off. So you can hear me now? Yeah, okay, good. So yeah, I was saying I would like to thank you both of you for inviting me here because since I'm a local, it's important for me to participate some way. So thank you very much for this opportunity. So I would like to present you some recent results I got with Carolina Rey from the University of Buenos Aires. About it's still an ongoing work, but we've got some results, and they deal with some non-local equation with critical growth. So just let me make a very brief introduction about non-local equation. So the most famous non-local operator is the fractional Laplacian, which is the operator you get by minimizing this non-local energy, right? And you can get a nonlinear version of this non-local energy just by replacing all the 2's by p's. And what you get when you minimize this nonlinear non-local energy is what is called the fractional P Laplacian. And in the limit when s goes to 1, the fractional differential order s goes to 1, then you recover the classical Dirichlet energy and the classical Laplacian and P Laplacian. This is a very famous result by Brezis, Bogami, Ionescu. And yes, very famous. And so equation with fractional Laplacian, fractional P Laplacian, there have been a lot of work about them since the publication of paper in around 2006 by Luis Caffarelli and Silvestre. And from that point on, there have been a lot of work dealing in general with non-local equation, non-local functional spaces. And in particular, what I would like to study equation of the following form, right? Here, my operator is this one, LK, which is like a fractional P Laplacian, but maybe slightly more general, because maybe we will replace the fractional kernel for the fractional P Laplacian by a case slightly more general. But there are still a lot of results for this kind of equation on our N or a bounded domain of our N with some boundary condition, Dirichlet, Neumann. There's been a lot of work. And what I would like to study is this kind of equation, but on a Riemannian manifold. My manifold will always be compact from that point on. So just I avoid every problem with unbounded manifold. So a compact Riemannian manifold M with a metric G. Right? And I would like to see what we could do with this kind of equation on manifolds. And yeah, of course, it's a very natural question because there have been a lot of work about equation on manifolds for their geometric interpretation. But still, this is quite, for fractional P Laplacian, it's quite a recent subject because as far as I know, the first result in that direction is due to the three guys, Guo Zhang in 2018. And they introduced what at first sight should be the right fractional Sobolev spaces, this one here, WSP, because you see these are all the functions in LP with finite energy, right? And in our N, here we had the norm, the Euclidean norm between x and y, the distance between x and y, and now we are on manifold. We just replace this Euclidean distance with the distance associated to the metric of the manifold. So it's the right generalization of what happened on our N. They put the obvious norm and they prove that the spaces satisfies all the expected properties. yeah, like density of smooth functions or reflexivity, separability, all that can be expected from good software spaces. And in particular, you get the class standard Sobolev embedding with the critical exponent here. Okay, so just I write it P star because I will be using it a lot. And just remember that this embedding is continuous when Q is less or equal than P star, and compact if Q is less than P star, strictly less than P star. And so once we got that, it's quite easy to come back to an equation like this one. Yeah, Guo Zhang did not study exactly this equation. Maybe they study a slightly simpler equation, but anyway, the result can be adapted to this kind of equation without much problem. And it works well because they do everything in the subcritical case. When Q, the growth of the right-hand side, is subcritical, because in that case, you can apply the mountain path theorem without any problem because you got compactness. So the main problem is what happens when you lose that compactness, when Q is equal to P star. So this is the first equation. You've got this equation on manifold, you've got a good Sobolev space to study this equation, and you've got a critical exponent, and you lose the compactness. So this is not trivial. But still, there is another question, maybe more fundamental, we can study, because Guo Zhang introduced this Sobolev space, this fractional Sobolev space, WSP, which is good, which is fine, which should be the right. But at this, like 15 years ago, Tribel introduced the whole scale of trivial Isokin and Bezoff spaces on manifolds. And among this big scale of spaces are what should be the right Sobolev fractional spaces. And his definition is very similar in spirit, of course, but it's not exactly the same as the WSP space of Guo Zhang. So we got this first question to compare the space introduced by Tribel and the space introduced by Guo Zhang, just to check if they are the same or not. They should be the same because they've got the same feeling behind. But when you look at the definition, it's not that obvious. And once we settle this question, we will come back to this equation and try to get some inspiration from what have been done over the last 20 years about equation with a critical growth to obtain some first results. Right? So just let me begin with the functional framework. So on the one hand, I've got this fractional space, the one introduced by Guo Zhang, good one, natural one. And on the other hand, I got all the spaces introduced by Tribel 15 years ago. And the trivial Isokin spaces on manifolds that Tribel introduced, they are modeled in a very natural way on the common trivial Isokin spaces on Rn. So I didn't put the definition of the spaces on Rn because it's quite awful, and I don't precisely need their definition, but only some properties of them. And the definition on the spaces on manifold is quite natural. You cover your manifold with charts. These are this function psi j. You localize your function in each chart, looking at f times psi j. And then you come back to Rn using the exponential chart. Right? So it's natural. You are in Rn, you put the trivial Isokin norm on Rn in your norm. Okay, so when you deal with Sobolev spaces, common Sobolev spaces like W12 on manifold, this is what you do. Right? So, but the point is that when and once you've got the trivial development spaces, you've got, by interpolation, some base of spaces. And when Q is equal to P, when you are now in Rn, then the trivial isorkin and the base of spaces coincide, and they both coincide with this space in Rn. So in Rn, everything coincides. But on a manifold, I've got this space and this one with Q equal to P. And it's not very clear they are the same. Not clear, at least for me, it's not clear at all. But still, trivial proved a lot of stuff for the spaces on manifolds. And among these, all the many properties it proved are the following one. First, really, when Q is equal to P, the trivial isorkin space coincide with the base of space. So exactly the same as in Rn. And these should be good fractional Soler spaces. And the second property it proves, which is the one I most care about, is like a property of localization. It proves that if you take some partition of unity for your manifold, then you can recover the norm, the triple isorkin norm of a function, only looking at the norm of this function localized through this partition of unity, which is not that obvious as a property because usually all these trivial isorkin spaces, base of spaces, are non-local in essence. So a property of localization, just like this one, is not obvious at all to get, but it can prove it. And what we did with Carolina to try to see if trivial spaces coincide with Guangzhang and Zhang spaces, we just tried to first mimic this kind of localization property. And we could prove that Guo-Zhang and Zhang space satisfies the same kind of localization property. And the good thing is that now you can localize. You can use some exponential map to go back to Rn locally. On Rn, you know that these spaces coincide with the WSP, and with a little bit of manipulation, at the end you can prove that really both Guangzhang and Zhang space W as SP coincide with these spaces introduced by Trill, which is good because now I'm sure I've got one good fractional Soler space. At the beginning, I had two candidates, both of them good, both of them with good properties, both of them natural, but it was not that obvious they were the same, and they are the same. So that's good. So now I've got one good space, and in particular, I've got all the theory developed by Tribble. Tribble did all the stuff. So I got everything. So, but still, I will always keep with the definition of the WSP given by Guo, Zhang, and Zhang, because it's the most intuitively, it's the most easy definition. I prefer this one as compared to this one. So now I've got a good functional framework. I would like to come back to my equation. So the kind of equation I'm interested in is this one. So H and F are just function coefficients, good one. I will put some usually assumption on them later. P is given greater than 1. And the Q, the growth of the right-hand side, will be also critical or critical. And my non-local operator, LK, comes from minimizing this energy. Where here the kernel K looks like the kernel corresponding to the fractional P Laplacian, meaning that I will assume it's symmetric and as singular as the kernel for the fractional P Laplacian. Right? So it's not a big generalization, it's almost the same. But it doesn't cost much. And of course, when Q is subcritical, when Q is less than P star, then you've got a compact embedding of WSP into LQ, and you can use all the classical theorem or variational analysis to get a solution on with reasonable assumption on agent F. And essentially, it's what Wojan and John did in that paper. Well, it's not exactly the same. They didn't consider exactly the same equation as this one, but you can adapt everything without much problem. So the main point is, what can I do if Q is critical? And moreover, why do I care for Q critical or not, besides a mathematical difficulty? And when you look at a critical equation with the Laplacian or the P Laplacian as an operator, it's because there was a big geometrical problem in the 80s, 90s, known as the Yamabe problem, which is a very famous problem in conformal geometry, which is the following one: you've got your manifold with a metric G, and the scalar curvature of G is a function, maybe a priori not constant. And Yamabe asked if you could change the metric G for another one, G tilde, which should be a multiple of G, something like a positive smooth function times G, in such a way that your new metric has constant scalar curvature, or more generally, is as a prescribed scalar curvature. And so this means that you have to look for a function U here. And when you write the relation between the scalar curvature of J and J tilde, you've got this equation for you, where the critical exponent appears. So this is the main motivation historically for studying critical equation. And this is not getting a non-trivial equation, non-trivial solution for this equation is not a trivial problem, because since this is the critical exponent, you have not compactness here. And so this problem was solved in a series of papers by Trelinger, Aubin, and Schoen, and later on, there have been a lot of work to extend their result in a lot of settings. But what I want to emphasize of all these papers, all these results, which are very, very technical, is the main idea of Thierry Aubin was to use an optimal Sobolev inequality, an inequality that quantifies precisely how W12 goes into L2 star. This is this inequality. And the most important part of this inequality is the constant you put here. Epsilon could be any arbitrary small positive number. And you need to find the least constant here, because the lower this constant, the better you will be afterward. And this constant is precisely given by the Sobolev embedding in Rn. And in fact, so Aubin proved this inequality. He proved that this constant here is the least possible one. And from that point on, there have been a lot of work dealing specifically with inequalities like this one. For instance, you can prove that this inequality is true when epsilon is equal to 0. You can replace all the 2's by p's. So you've got the same kind of inequality for higher orders for spaces like W22, or for functions which have some symmetry. So there have been a lot of work, and more generally, there have been a lot of work concerning equation with Laplacian with a critical growth on manifold. Okay, so but anyway, so I'm interested in this kind of inequality, but in a non-local setting, meaning that I would like to replace this local norm here by a non-local energy, right? And of course, there have been a lot of work for equation with a fractional operator, like fractional Laplacian, fractional P Laplacian, or on Rn with critical growth. And I put here some very few people, too few. They are just entry points, because this is a very vast literature, and I put here some friends, some colleagues from here, from Buenos Aires and San Luis, and who are working on this kind of problems too. So there's been a lot of work about that. But maybe that, up to my knowledge, there haven't been many work for fractional P Laplacian equation on manifolds. So that was our main motivation with Carolina. And if we try to mimic what Aubin did, for in the case of the Laplacian, we need an optimal Sobolev inequality, but with a non-local energy. And we've got this, fortunately, we've got this non-local optimal Sobolev inequality, which it's almost the same one as Aubin proved, because you can control the LP star norm, P star is a critical exponent of a function u, by, well, so the LP norm of u, of course, and also you have here the non-local energy. Just remember that when S goes to 1 or is equal to 1, this becomes the integral of the grant of u to the power p, so the common local energy. So we've got exactly the right good optimal Sobolev inequality, and when p is equal to 2, the constant here is the least possible one and is given, as in the local case, by what happened on Rn for the fractional Sobolev embedding in Rn. Sorry, this should be a p star. Okay. And when p is equal to 2, we could prove that this A is the least possible one by some test function computation. Because when p is equal to 2, you know what are precisely the minimizers in this optimal inequality here. But when p is different from 2, you don't know them precisely. And what is known is, up to now, is not enough for us to do the same kind of computation. But still, we guess that for any p, this A, the best possible A in the fractional inequality in Rn should be the least inequality here. This should be this one. Okay, so now I've got this inequality. I would like to come back to my equation. But if you remember, in my equation, I wanted to consider a kernel slightly more general than this one. So I need here to replace this distance by a kernel k and see if we can get something, the same kind of inequality with a k here and not this distance. And in fact, we could do that under some assumption. Okay, so the first two assumptions are expected. I will take my kernel k to be symmetric and to be as singular as what happened for the fractional P average. Okay, not much singular, not less singular. And there is another ingredient I need, which is that in the proof of my optimal Sobolev inequality, I needed to make some local test function computation. And to do this computation, we needed to make a blow-up of the manifold at a given point. A blow-up only means that if you take a point, x0, say, you just make a zoom of the manifold around this point. So precisely from the point of view of the metric, what you do is you use the exponential map at x0 to pull back the metric on Rn, and then you make the dilatation. And I need my kernel k to behave well, in some sense, under this kind of blow-up of the manifold. And to behave well is the following. This means that when I do my blow-up, then the kernel I get after the blow-up and with a good rescaling should converge to the kernel corresponding to the fractional P Laplacian in Rn with a good convergence. So this is exactly the technical assumption we need to adapt the proof to a more general kernel K. And this kind of assumption is satisfied in particular by obviously this kernel, and also this kernel when perturbed by a less singular perturbation. Because in the end, when you do the blow up and you scale multiplying by this factor, then this absorbs this less singular part. And so under this assumption on my kernel K, I can get exactly the same kind of optimal Sobolev inequality, except that now here I got a slightly more general non-local nonlinear energy. So now I've got this one. Really, I can come back to my equation, which was this equation where the operator here, Lk, comes exactly from minimizing this energy, exactly the energy appearing in my Sobolev inequality. And then I can try to do exactly the same steps as Aubin did in the case where here you had a Laplacian. And from this point on, once you have this optimal Sobolev inequality, it's quite classical, because to get a solution, you consider the obvious functional associated to the equation. You try to minimize it over this set here, which is what you did in Rn, obviously. And to get the existence of a minimizer, you need some condition on J, on the functional J. And using the optimal Sobolev inequality and using exactly the same steps as Aubin's steps 20 years ago or more, which are very classical, you can prove that if your functional is, its infimum is low enough, where here you can see 1 over A being the constant here. That's why you need the least possible A, because this gives you the bigger possible 1 over A. So once you've got this strict inequality, because the large inequality is more or less always true, but the point is that you need the strict inequality. Then you can prove you have a solution to your equation. And now, usually, you make some test function computation to estimate this infimum. And here is where what we did up to now is not that satisfactory, because when you are dealing with equation manifold with a Laplacian or a P Laplacian, you can make some fine test function computation and get a nice local estimate of this infimum and obtain a good sufficient existence condition, mixing the coefficient of the equation with the local geometry of the manifold. But the point is that since this energy here is non-local, all the test function computation are much trickier. And up to now, what we could do is not that satisfactory. We took the easy way, and we estimated the infimum of the functional by a constant test function, which is not at all satisfactory, but at least we can get some useful existence condition, because you've got a precise condition relating all the coefficients of the equation with the constant A appearing here in your optimal Sobolev inequality. So this is good because we've got an explicit condition, but this is not satisfactory because we would like to have a local condition, meaning that I would like to have a condition mixing the value of A, of F, and H at a given point, X naught, with the geometry of the manifold at that point. So this is what is still lacking, but it's not easy to make good test function computation. But still, the good thing is that from now on, since we've got this optimal Sobolev inequality, we can try to, in the future, we try to mimic, to adapt all the classical results that hold when you got here the norm of the gradient For instance, we could try to prove if this inequality is true when epsilon is equal to 0, because in the local case, this is true, but in the non-local case, it's not that obvious. We could try to see what happens when we send p to 1. In the local case, you get at the end some kind of isoperimetric inequality, which is nice. And in the non-local case, in our M, there is a notion of non-local perimeter, but not on manifold. So it's a bit interesting to see what happens in that case. And so the good thing is that now we've got a good functional framework with a good space. We've got nice optimal Sobolev inequality, and we can do something with a non-local nonlinear equation with critical growth, which was not available to now. So, well, thank you very much for your attention. And I'm good.
Thank you very much. So,